Bismillah ar-Rahman ar-Rahim. Welcome to Tahar Scholar. We are الخميس 26 أكتوبر 2023 بماليزيا. Or in English, Thursday 26th October 2023 in Malaysia. We are still in our series Programming with Matlab, and this is practical number 3. We will dedicate practical number 3 and practical 4 to the data type string, because in this topic there are many details, and I do not want to film a long video that it will be difficult to follow. So I subdivided the topic in two practicals. In this first practical, we will see section 1, UTF encoding, how to store characters and strings in memory. This section is about that topic. And then in section 2, how to build the strings and how to concatenate them. And the third, the fourth, and the fifth section will be in the next practical. The third section, we will discuss some utilities dedicated to strings. Then section 4, formatted strings, how we format a string. And the final section will be a script to practice what we have learned on this topic: strings, data type strings, data type string. Strings are less important than matrices, and we have dedicated two practicals to matrices. But still, it is important to understand how characters are actually stored in memory and how we manipulate them. So let's start our practical. This is practical number 3. We start with section 1, UTF encoding. UTF means Unicode Transformation Format. In Unicode Transformation Format, we establish a mapping between characters and integers. Characters are stored in memory as integers. To each character corresponds an integer. How this is being done? It is done in a standard fashion, and it is called the Unicode Transformation Format. It's a huge table. To each character, there is an integer. So let's see an example here. I have written them here, some of them. So some Unicode of some characters. We start with uppercase letters. The character A is stored as 65, the integer 65. The character B as 66, and so on till the character Z or Z is stored as 90. The lowercase letters A, B, until with following integers 97, 98 till 122. And the digits 0, 1, 0 here means the character 0, not the integer 0. The character 0, the symbol 0, that we draw in a text. We display in a text. The symbol 0 is stored in memory as 48. The symbol 1, or the character 1, is stored as 49. Then 2, 3 till 9. 9 is stored 57. They are subsequent. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 48, 49, 50, 51 till 57. There are 10 digits in the decimal base. This mapping from characters to integers is a little bit old, It was called the ASCII, the American Standard Code for Information Interchange, the ASCII. I write it here, the ASCII. ASCII is a little bit old, and it was very limited. It can accommodate only 128 characters, from 0 till 127, which is, of course, very limited. There are many, many, many letters in many, many languages, human languages, mathematical symbols, etc. Impossible, of course, but that was the start. When computer science started, there was only English, American English, and some digits and mathematical symbol like plus, minus, etc. So the table, the ASCII table, was very limited, insufficient. And there was research to standardize that, and they come with a larger table. So many, many letters, thousands of letters have been encoded, gradually encoded. It took several years. So, for example, the Greek alpha, the letter alpha, is encoded with the number. Here I give the number in hexadecimal base, like in the standard. The standard, they don't give the number in the decimal base. They give it in hexadecimal base because it is shorter. And generally, you will find that in bibliography, they note it U plus, and then they give the number in the hexadecimal base. The number in the hexadecimal base. But in Matlab and C++ and many languages, hexadecimal are represented with 0x. 0x, not OX. Let's see that with a calculator to see the number in the decimal base. So I have here a calculator. I use the interface for programmer. You have, this is on Windows. You have standard, scientific, graphing, programmer, and date calculation. I chosen programmer to see the different bases. Hexadecimal is base 16, decimal base 10, octet base 8, and binary base 2. So the base hexadecimal 3B1 for alpha, 3B1. It is equivalent to 945 in the decimal base. And here it's formed in octet base, and it's formed in the binary format, or the binary base. So it is an integer. It's just the base used is hexadecimal in the standard. This Unicode, this code points, these integers associated to characters are standard. They are standard, and you can find them in Wikipedia and in many resources in internet. So this is for beta, gamma, theta, lambda, p. This is an emoji. It is very small. It is the writing hand. You can type, for example, in the internet, you can type character U plus, and then you give the hexadecimal number, the number in the hexadecimal base. That is 27, 0D, and you will find the writing hand. It is an emoji, as I said. Another character is the Egyptian hieroglyph. It has, of course, a meaning, but just to show you that there are many, many, many characters. Actually, in the standard, there is 1,114,112 code points. These code points are actually distributed through planes. There are actually 17 planes. The basic multilingual plane and 16 supplementary multilingual planes. They have all the same number of code points. They can accommodate the same number of code points, which is 2 to the power of 16. That is the number of integers we can store in 16 bits. Because a bit can be 0 or 1, so the number of integers we can store in 16 bits is 2 to the power of 16. So in the basic multilingual plane, the code points go from 0 till 2 to the power of 16 minus 1, which is equal to 65,525. So thousands of code points per each plane. And the total is 1 million, as I said before, 1,114,112. And actually, not all code points have been assigned a character. There are still room for more characters to come in the future, but this is the maximum that could be considered as a code point by the standard, the current standard. Now comes the problem is how we can store these integers, how we can store these code points. Because an integer can be stored by bytes. A byte is 8 bits, so we can store in 1 byte, 2 bytes, 3 or 4 bytes, or even more. And we say 8-bit integer, 16-bit integer, 32-bit integer, and 64-bit integer. So to accommodate, to store all these code points in memory, we need normally 32 bits. 32 bits. Even if small code points need only, in ASCII for example, need only 8 bits. So this will be there will be a waste of memory if we code all the code points in 32 bits. And some researcher in this field proposed different schemes to store integer. The most important encoding, and they are standard now, are called UTF-8 and UTF-16. So let us see first UTF-8 and then UTF-16. Let us save here and go to UTF-8 encoding. So in UTF-8 encoding, a code point can be stored in 1 byte, in 2 bytes, 3 bytes, or 4 bytes, depending on its value. So if it's small, small means between 0 and 127, we can code it in 7 bits. This is a byte with 8 bits. The first bit is reserved, is always equal 0. The first bit is always equal 0. And we have 7 bits to store an integer. So how many integer? It's 2 to the power of 7. 2 to the 7. Because each bit can be equal to 1 or to 0. And we have 7. So the number of digits that can be stored are 2 to the 7, which is 128. Or in hexadecimal, 0x80. So the Unicodes in the range 0 till 127 can be coded in 1 byte. And actually these are the ASCII code, the ASCII characters. Let's see them here in, we have a program called character map, as you can see here. All these characters till this one, till U plus 007, you can see all these characters. Let's select them. We cannot select all, but from this one till this one, they need only the integer that they represent need only 1 byte. They can be stored in 1 byte. Their code point can be stored only in 1 byte. They don't need 32 bits. That is 4 bytes. A byte has 8 bits. They don't need 4 bytes. They don't need 32 bits. It's a waste of memory. So, but one example is the letter A, 65, its code point, and it is stored as follows, because 65 is in binary base is this number. So 0 is reserved, and we assigned the bits this value, 10001. And you can check also with the calculator. 65 in binary is 010001, as here, like here. So if the code point is greater, of course, than 127, 128, 130, 200, etc., we need more bytes. For 2 bytes, we can store the following. So there is a format for UTF encoding. In 2 bytes, the first byte is called the leading byte, and the second byte is called the trailing byte. The leading byte, the first bit in the leading byte, tells us that there is only one trailing byte. If it is 0, if the first bit is 0, we have no trailing byte. If it is 1, there is 1 trailing byte, and then the 2 bits, the 2 subsequent bits are always 10 in the leading byte and in the trailing byte, always 10. They are reserved. So what we are left with is the following bits that I noted here by X. We have 5 bits in the leading byte and 6 bits and beg your pardon, and 6 bits in the trailing byte. So 5 plus 6 is 11. We have 11 bits. How many integers we can store in 11 bits? Is 2 to the power of 11, which is 2048. We can store 2048 code points in 2 bytes. And here the corresponding value in hexadecimal base. So the Unicodes in the range 128 till 2047 can be stored in 2 bytes. Or here in hexadecimal. I have written the range in decimal base and in the hexadecimal base. For example, let us take alpha, the Greek letter alpha. Its Unicode in the standard is, as I said before, is 0x03b1 in hexadecimal base. In binary format is the following. We transform hexadecimal in binary format. But how we can store this in UTF-8? In 2 bytes, as I said. The first 3 bits are reserved in the first byte, in the leading byte, and the first 2 bits in the trailing byte are reserved. So what we do, we take the first 6 bits, 1, 2, 3, 4, 5, 6. The first 6 bits of the code point, the first 6 bits, we store them in the trailing byte, as I have done here. And then the rest of the bits, we store them in the leading byte. We start from the trailing byte and then the leading byte. This is the mapping. This is the rule. Always. you have the Unicode in binary format. Take the first 6 bits, store them in the trailing byte, and then the rest store them in the leading byte. These bits, the first bits, 110 and 10, are reserved. You cannot modify them. The rest, this one, the 5, and the 6, it depends on your Unicode. Any Unicode between 128 and 2047 can be stored in 2 bytes, or in hexadecimal between 80 and 07FF can be stored in 2 bytes. And what about the others? The others, we need more bytes. So we have here 3 bytes. In 3 bytes, we have the leading byte and 2 trailing bytes. And as you can see here, the first bits, we have 1 and 1, means we have 2 trailing bytes. And then comes 10. So we have 2 trailing bytes. If it was only 1 trailing byte, we get 110 in the leading byte. If there is no trailing byte, we get 0. Our leading byte, the first bits of our leading byte tells us how many trailing bytes there are. If it is 0, there is no trailing byte. If it is the sequence 110, there is 1 trailing byte. If the sequence of bits in the leading byte is 1110, there is 2 trailing bytes. And trailing bytes always starts with 10, the sequence 10 and 10, always. This is the UTF encoding. This is the mechanics of UTF, the mechanism of how we store bits in UTF-8 encoding. So how many bits we have? We have here 4 and 6 and here 6. So 14, no, 6, 12, and 4, we have 16. We have 16 bits to store our code point. 2 to the power of 16 means we can store in these 3 bytes 65,536 code points, or in hexadecimal, the following value. So we can accommodate in 3 bytes Unicodes in the range from 2048. 2048 cannot be stored in 2 bytes because it's not in the range of 2 bytes. So it starts from 2048 till 65,535. An example is the emoji of the writing hand. Its Unicode is 0x270D in hexadecimal base. In binary, 0b, the binary always starts with 0b, and hexadecimal, the notation starts always with 0x in Matlab or in C++ and other languages. And this is its binary value, the value in the binary base. How we can do that? We start with the 6 digits, 1, 2, 3, 4, 5, 6. 6 digits, we put them in the last trailing byte. And then the subsequent 6 digits, 3, 4, 5, 6, we put them in the second trailing byte. And then the rest, that is 0, 1, we put it in the leading byte. And of course, as I said, the first bits are reserved always according to the UTF encoding. So 110 is reserved. We don't modify. We don't have the right to modify. Then 10, and the rest we fill them according to the Unicode in the binary base. And if our code point is not in this range, is greater than 65,535, then we need 4 bytes. And for 4 bytes, there is 3 trailing bytes, and this must be coded in the leading byte. So we have 1, This is the first trailing byte, second trailing byte, third trailing byte. And then comes the sequence, always 1 0. Before we put our bits, always 1 0. Same, 1 0, 1 0, and 1 0. So this is the format of encoding for 4 bytes. How many bits we have? We have 6 here, 6, 6, 18 plus 3. So 20, 21. How many integers we can store in 21 bits? It's 2 to the power of 21, which gives the number 2,097,152. It's huge. It's actually larger than the standard. Standard proposed 1 million and a few 100,000. So, and I have also given the range from 65,536 to this value -1 to here -1. I made a mistake. And the corresponding hexadecimal. Let us check here. We can use Matlab to transform that into hexadecimal. We use a function. Let's go to Matlab or to Octave and come back. We use a function called dec 2x decimal to hexadecimal, and we give the number in decimal form and we get it in hexadecimal form. And as you can see, it returns actually a string. This is a string 0, it's string 1ff 5f's. Let's write it again, this time in hexadecimal format, 0x 1 FFF 5, and we get the same number as we have given here. So 0x 1FF or 2,097,151 is the same. It's the same number in memory, the same value in memory, but here in hexadecimal base and here in the decimal base. So let's come back to our notes. What we have here exactly. So I have made a mistake here, but not here. So this is the range. Any Unicode in this range need 4 bytes. It cannot be stored in 3 bytes. And an example is Egyptian hieroglyph, which has the Unicode, the following Unicode from the standard. This is standard. This is given from the standard. Unicode is always from the, you call that Unicode or code point the same. It's from the standard. It's from the standard. And we are here interested how to store that number in memory according to UTF-8 encoding. So let's come back. We have here the binary. So the first 6, 1, 2, 3, 4, 5, 6. We have them here. 1, 2, 3, 4, 5, 6. And the sequence 1, 0 always. Then we go to the second trailing byte, and then the third trailing byte, and the rest we store them in the leading byte. So let's do that. Let's do that. What we have here: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then 1, 2 on the rest. So this one is stored in the third trailing byte. And the leading byte, 0. We store only 0. We have only 3 places we store 0. The rest is reserved. We don't modify. We have not the right to modify. These first digits, we don't have the right, bits, we don't have the right to modify. They tell us that there are three trailing bits, that there are three trailing bytes, and then the sequence must start with 10, with 1 0, 1 0, 1 0, 1 0. And that's it, and that's it. It's very simple. If you are not familiar with binary, you can stop the video and repeat again this section to understand it more carefully. So what I have written here, all ASCII code points are in the first range and are encoded in 1 byte because they are less than 127. That means that UTF encoding is compatible with ASCII. We use the same technique to store characters in the ASCII as in UTF-8. The same, because they are all less than 100 or equal to 127. All BMP, the basic multilingual plane, that are not in the ASCII range are in the second or the third range, like alpha or the emoji. We can store them in 2 bytes or in 3 bytes. And the rest, the 16 supplementary multilingual planes are in the 4th range. We need 4 bytes to encode them in UTF-8 encoding. So the basic multilingual plane contains the majority of human languages currently used, like Arabic, Chinese, part of Chinese and Korean and Japanese. Not all symbols in Chinese are represented in the BMP. So the rest needs, of course, more memory, more bytes. So this is for the UTF-8 encoding. So we continue with UTF encoding. We have seen in UTF-8 the storage unit is 1 byte. We can store code points, Unicodes, in 1 byte, 2, 3, or 4 bytes, according to the value of the code point. In UTF-16, the storage unit is 16 bits, is an integer, an unsigned integer of 16 bits. Unsigned means positive, strictly positive. And as you can see here, in this unit, integer 16, we can accommodate 2 to the power of 16 integers. That is 65,536 unsigned integers. So in this encoding, in UTF-16 encoding, we can store all the characters or all the code points in the BMP, in the basic multilingual plane, in 1 unit, in 1 single unit. While all the code points in the 16 supplementary multilingual planes need two units called surrogate pair. 2 16-bit integers called surrogate pair. So in 1 single unit, actually not all the range from 0 till to the power of 16 minus 1. This is the range of all integers that can be stored in 16 bits. It's not all this range that is dedicated to code points, because there is a range, inside that range, from 0x D800 till 0x DFF. This range is reserved to surrogate pairs. When we store in 2 units, in 2 16-bit integers, we need that range. So there will be no confusion between code points in the basic multilingual plane and code points in the SMPs, in the supplementary multilingual planes. So the integers in this range cannot be code points. And hence, our range of code points for multilingual plane must be from 0 till 0x D800 minus 1, that is 0x D7FF, and from 0x DFF plus 1, that is 0x E00 till 0x FF. So this is the limit, the end points of the range where code points can be used for characters. And I have written it here in the decimal place. An example, the letter A, the letter alpha, the emoji, the writing hand, all are stored in one single integer 16-bit integers. I will say uint 16, in one uint 16. Without any mapping, without any modification. They are stored as they are. And this is one important advantage of UTF-16. There is no mapping at all. The Unicode is stored as it is in that storage unit. For characters outside the BMP, that is in the SMPs, we need a pair of two integers of 16 bits. So a surrogate pair XY, such that the first element of the pair must be in this interval 0x D800 till 0x DBFF, and the second must be in the 0x DC00 till 0x DFF. So both x and y are in the range that we have reserved for surrogate pair. How we do that? There is a mapping for that, a little bit complex, that use shifting of bits. You can check if you want in Wikipedia. There is details how to do that. At any code points outside the BMP, we can associate a unique pair. By that mapping, by using that mapping, we can associate a unit pair that define that code point without any ambiguity. And the x and y are 16 bits, but they do not represent code points because they belong to the range that we have reserved to surrogate pairs. So they cannot be code points. X and Y can never be code points. So, for example, the Egyptian hieroglyph, which has as Unicode 0x01300A from the standard, we can associate a pair using a mapping specific to this encoding, and we get x and y, these two values. And they do belong, x belong to the first element of the pair, belong to this range, and the other second element of the pair belong to this range. So this is for UTF-16 encoding. Why is this important? Because in Octave, we use, or they use UTF-8. In Octave, strings characters are stored using UTF-8 encoding. While in Matlab, the official Matlab, they use UTF-16 encoding. They don't use UTF-8. And there is, of course, pros and cons, but the main advantage of UTF-16 is that, as I said, all the characters in the BMP needs only one storage unit. So one integer is a character, and a character is an integer. While in UTF-8, a character is not an integer because the storage unit is 1 byte. So a character is a multi-byte integer. It can be 1 byte, 2 byte, 3 byte in BMP. It needs 1 unit, 2 unit, 3 unit. So that's the main difference. Let's come back to Octave and see two important functions that give the UTF-8 encoding of any character, and vice versa. If you give the UTF-8 encoding, you get the character. Those two functions are double and char. So for example, double of character A gives us the UTF encoding of A, which is 1 byte, 65. And for example, of character 0, we get the UTF, the Unicode, because it is an ASCII. So 1 byte. But what about alpha? Let's copy alpha and come back. Here we get 2 bytes. Because as we said, characters can, in UTF-8 encoding, can be encoded in 1, 2, 3, or 4 bytes. For alpha, we need 2 bytes. And we can see them in binary format. We use decimal to bin, and we give the vector of the 2 bytes, 206 and 177. And we get exactly what we have seen before when we explained UTF-8 encoding. Let's write them here. So they are exactly the same as we have explained before. We have the sequence of the reading byte, 110. It tells us that there is one trailing byte and then 10, and the trailing byte starts with 10, and the rest are the bits that represent the Unicode. So double will return for alpha, it will return the UTF-8 encoding of that letter in 2 bytes. Okay. And now the opposite, or the inverse. If you give the UTF-8 encoding, you get the character. So we write char and the Unicode for ASCII, we get A. The Unicode for 0, for the letter 0, we get the letter 0. For alpha, we don't give the Unicode, we give the UTF-8 encoding, because the Unicode is encoded in 2 bytes. We can give that in binary format like this, or we can give it in the decimal format the same. I copy paste. Exactly the same. So we have double and char to convert from the character to its UTF-8 encoding. And with this, we finish the first section, UTF-8 encoding. UTF means UTF-8 and UTF-16, and we said that UTF means Unicode Transformation Format. It's mainly a big table that associate to each character a code point, and we have seen that we can store that code point in UTF-8 or in UTF-16. In UTF-8, the storage unit is 1 byte, 8-bit integer, while in UTF-16, the storage unit is 16-bit integer. And an important observation is that Octave use UTF-8 and Matlab, the efficient Matlab, use UTF-16. So double and char will give different results in Matlab, in the efficient Matlab. You will get, for alpha, you will get the Unicode, one integer, because it is in the BMP. So Let's clear the console and the memory, and we move to the second section. So in section 2, dedicated to the data type string, we see how to build strings. So let's say, for example, S equal, and we use here the double quote, and for example, hello, and we close the double quote. So it's between double quotes, and we add semicolon, we display the string. So actually S is an array of bytes, not of characters, of bytes. Here, because all the characters are in the ASCII range, each character is actually a byte, is stored, its code point is stored in 1 byte. So let's see, for example, how many bytes is there. Num element of S, we get 6, and we have 6 characters, because the character here is 1 byte, is coded in 1 byte. 1, 2, 3, 4, 5, 6. We have 6 characters, 6 bytes. We can also store the same string using a single quote, the same string. Same num element so in the official Matlab, actually there is 2 types of string. There is a class string and a string as an array of characters. But in Octave, it's always an array of characters. There is no class called string currently in Matlab, in Octave. So now let's try another string, but that contains characters that are not in the ASCII code. They are in the BMP, but not in the ASCII. So for example, let's copy paste here. And we have our string, double quoted, alpha equal 10 degrees, comma, beta equal 0.5 pi. And we type enter. So here it is also an array of bytes. How many characters we have? 1. The space character is also a character, space character. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have 18 characters. But if you call num element of A, you will find another number. You will find 22. Because the character alpha, the character degree, beta, and p are encoded in 2 bytes, as we have seen previously in first section. In UTF-8, they are encoded in characters are encoded in 1, 2, 3, or 4 bytes. For these specific characters, alpha, degree, beta, and p, they are all encoded in 2 bytes. So when we count, we add 1 byte, 1 byte, 1 byte, 1 byte, so 4 plus 18 characters. And we get 22, of course. So the array here is an array of bytes, not an array of characters. If you call, for example, S, all the elements of S are in ASCII. If you say S1, it is the first character, because the character here is encoded in 1 byte. If you say S2, the second element of S is a byte. It is also a character. It is E, because here character and bytes are synonym. But if you say, for example, A1, the first element of A, it is alpha. No, it's not alpha. It is the first byte representing alpha, and you got an invalid character. You got this is the symbol of an invalid character. You get an invalid character because this is the first byte representing alpha, the leading byte. It is not a character. It is not a character. The character is in 2 bytes. So what we do the following. We give we want our character in the 2 bytes. So first byte and second byte, and we get alpha. Same here, for example. So let's count 1, 2, 3, 4, 5, 6, 7. It is the 7th character, but it is the because we have to add 1 byte here. It is the 8th. It is the 8th byte. Let us try here and see what we get. The 8th and 9th byte. We get the degree. If we write only 8, we get an invalid character. See? So this is the important difference when you use Octave. The element of a string are not necessarily characters. They are characters only in the ASCII range. Outside ASCII range, they are bytes. They are a multi-byte character. In the official Matlab, all the characters in the BMP, only in the BMP, in the basic multilingual plane, which is of course huge. It's a huge range. Are integer 16-bit integers, so 1 unit. The element of a string is a character when you are in the BMP. So that's the important difference. Outside the BMP, in Matlab, you need, as we said in the first section, we need 2 integers. But inside BMP, a character and element of string are the same. So this is important to observe. There is another function here important, is called isChar, to check if our string is correct. There is no invalid character in S. It returns 1. 1 means true. And for A, same. It is true. All the bytes are correct. It is a valid string. But if you write, for example, is char, and you give a real number, for example, 125, you get, of course, invalid. It is not a character. It is a real number. You get 0. 0 means false. That's it for how to build strings. Let's move to concatenation. So for concatenation, let's use as data the following fruits. I have copy and I pasted them here. Peach, pear, pineapple, plum, and pomegranate. And I store them in the variable b1 till b5. And I want to build a larger string containing all these fruits. I use concatenation. So I write b equal square bracket. They are matrices. This is a row vector, a row vector, a row vector, and the elements of our bytes are integers that represent characters. As I've said again and again, a character does not mean necessarily a byte. It can be a byte, 2 bytes, 3 bytes, or 4 bytes. Yeah, because all the characters are in the ASCII range, they represent also bytes. So, but even if they are not in the ASCII, it's okay. We build in the same way a concatenated string. So we write the first string, and we add the space. We add spaces between the strings. So b2 space, b3 space, b4 space, and b5. And we close the bracket. We can, of course, separate the elements of the vector by a comma for clarity. But it's not mandatory. You can use space character or comma to separate the elements of your vector. And we type enter. And we get a larger string, peach, pear, pineapple, plum, pomegranate in one single string. And we can calculate how many bytes are in our string, num element, 37 bytes. And here bytes means a byte means a character because we are manipulating only ASCII characters in the range of the ASCII. So this is how to concatenate to build a larger string. We can also concatenate to build a matrix of bytes. Let us call it C and equal brackets, and B1 will be our first row, then B2, then B3, then B4, and finally B5. And we get a matrix of characters. This is a matrix of characters. Each row is a string. But here observe an important thing, because a matrix has a fixed number of columns. So here if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we have 11 characters in the largest string. So each row contains actually 11 characters, 11 bytes. Each row. The rest of the characters here are space, and same here. So if we call size of our matrix, it is a matrix of bytes. We get we get 5 by 11. It has 11 columns. The rest, as I said, are filled with space character. We can also, here, if you can see, the strings are adjusted at the left. We can adjust them at the right or at the center in the matrix. For that, we use a string adjust. Let us call it D. String adjust. We give as argument our matrix of strings, and the second argument we give right, left, or center. So let's write here right. And see what we obtain. And as you can see, all the strings are adjusted to the right. And the rest, we call that the padding character. The padding character is a space character. The rest is padded with space character. We can also do adjust to the center and to the left. The default is the right. So if you call just string adjust, it will adjust the strings in the matrix to the right. This is the default behavior, and as you can see. So this is the end of the second section, how to build and concatenate strings. So see you inshallah next time in the fourth practical. Peace.